Hello everyone. Hello sir. Today's topic of video is GAN. So in this particular video, I am going to discuss in-depth intuition of the generative adversarial networks. So the agenda of this particular video is firstly we discussing the introduction of the GAN. Then we discuss some of the application of the GAN that gives you a good motivation to learn this topic. Then we discuss the concept of generator and the discriminator. Then we discuss the concept of the loss function, and at the end we are discussing the some of the problem associated with the GAN and the code implementation of the GAN on the CFAR 10 dataset. So this is the agenda of the video. So let me first start with the introduction part. So GAN stands for the generative adversarial networks. So the name itself suggests is generative means we are going to generate something. Why it is called adversarial we'll discuss in the upcoming video portion. And this is the network because it is a neural network, so that's why it is called a generative adversarial networks. So from this word generative we can able to understand that it's going to generate something. Okay, I hope till the point thing is clear to you. Now next thing is GAN is a unsupervised method. In the our machine learning community or deep learning, basically we have two type of method. One is supervised and the second one is unsupervised. In supervised learning we have input plus label, but in unsupervised we don't have any label. We only have just input data, and based on that data we are performing our task and all. So I hope this concept is already known to you, so I discuss further on the topic of GAN. So why we are calling it? So the question rises in your minds, why GAN is unsupervised learning? Why it is not supervised learning? So for understanding this, let's first consider one example where you classify image into two classes. Let's say so you have some input images. Let's consider an example of dog versus cat classifier. Okay, so you have some input images. You passes this input images to the convolutional neural network, and this convolutional neural network says whether it is a dog or whether it is a cat. Okay, so this is a typical binary classification problem where you provide a input images, it learns something from or learn some feature, and based on that feature it predicting it as a dog or cat. Means means 0 or 1. So this is the example of classification problem. But what if I am saying you that you have one input images, you pass this input images through the neural network, which is anything, convolution layer or RNN layer or fully connected layer, anything, it is a neural network, and you get output in form of the image, not in form of the any class like 0 1 2 3 or binary classification or multi-class classification. Again I am telling you, you pass the input, you make some processing using the neural network, and again in the output you also got the image. So in this entire process no labels are associated. That's why GAN is called unsupervised method. I hope till the point the concept is clear to you. So what is the objective of the GAN? Objective of the GAN is to generate something new from the data. Let's say you have given some of the data set, you pass this to the GAN. Again we are not going to discuss working right now, I am just giving you intuition. In the upcoming part of video we are also going to work entire architecture of the GAN and how GAN is working. Okay, so you have some data set, you pass it to the GAN and you generate something. So what is this something? So generate something new from the data set which is similar to the data set but not exactly the same. I hope this line is quite confusing to you, so I'll simply break down this and explain it to you in very easy manner. So let's take one example. Let's say you have a 1000 cat images. Okay, you pass this 1000 cat images to the GAN network. Now you again, currently we are discussing input and output, so you again got some cat images output. So the cat images which is generated by this GAN network, so the cat images generated by this GAN network is similar to this original data set but not exactly same. Currently I also think that something is not clear to you, but you can understand the cat generated from here is also looking like a cat, but it is, so it is also similar to the other cats, but it is not exactly same as given in this data set. It is something new from the data set. I hope till the point the everything is clear to you. So before moving on the working of the GAN, I want to discuss the few of the application of the GAN. I found one very good blog on this particular topic, so I am going to discuss it with you. So I'm going on my screen, and here is the some application of the GAN. Okay, so here it is showing generate a photography of human faces. Generate the photograph of human faces. So what we can generate a photograph of human faces means you have some real images, so you have some human photos, face images of some human. Okay, likewise this. Okay, so you have some human photo faces, you pass to GAN, and as an output you also got some human photo, which is this. So this is the output and this is the input. Let's consider this for now. And what if I am saying that this also looks like a human, this all are looks like a human, but what if I am saying you that this human not exist in the world, it is generated by the AI, generated by the GAN network. So it is also similar to this one, is also looks similar to the human, but this is not exist in the real world. So what GAN do is it's learn the distribution of this data, and using this data it can able to generate some new human photo which is not exist in the real world, but it is similar to the human. So this is one of the application of the GAN. The next application is this is again cartoon character generator, which is similar to the previous human face generator application. The one more application is image to image translation. So let's say you have input images, you have some ground truth images. So these two are your input and ground truth, and using these two images you can able to generate these kind of images here. So basically let's say you have some images, you have taken a photo of the some places at time of day, and you have taken a photo of the same place at time of night. Okay, and you want to convert the photo of evening. Okay, so means you have photo of this, you have photo of this, and you want to convert this kind of photo from this using this input and ground truth, then GAN able to generate this. This is one of the application. This is also one of the interesting application, like you have a input uncolored simple purse images, and as a output you got a very colorful purse. Like here is the shoes is normal black and white images, but as output you get a colorful shoes, colorful bags, So this is how you can see the power of GAN, how it is useful and how it is reduce the manual human work. Let's say you provide this image, then within some seconds it generate color on top of these images, which is actually, if a human can going to do this process, then it's take a require lot of works and efforts. So this is also similar. You have a horse in this particular images, and you can convert this horse into zebra, you can see. Now this is one of the other application of the image to image translation. You have this satellite map, and from this satellite view you can generate a map view. So from the satellite view you can generate a map view. So how beautiful is this, you can see here. There is some other application also. Some other application like text to image generation, means you providing some text to your model, and based on the text and based on the understanding, it generate the images like this. This is a one other application of the GAN. Although one another application like is this are also same. This is also image to image, like face front view generation, generating a new human poses. Like you have only these two poses, and based using these you can able to generate some new human poses. So this is helpful to the some marketing company or who want some model images, so they have to require less efforts. This is some other application like photos to emoji generation. So here is the photo and here is the emoji corresponding to this, means you provide this photo to GAN, and this will return you this emoji. What I say is, you provide this image to GAN network, and as output GAN return this emoji generated photo. So how beautiful is this? There is some another applications are also there. Like this is the important application. You have same faces, so photography edition, you can generate you can try different hairstyle, convert this female into the male version. You can also try different smile, like here it is not smile, like here you can generate some smiles. Here it is not smiling, but here you can able to generate a smile. You can try different hairstyle on top of the faces, convert this male into female. So these are some important application of the GAN. Like rain denoising, in this particular image you have rain are there, but you can using a GAN you can able to remove a rain from this image, and you can see the difference between first and second images. Likewise here C and D images you can able to differentiate in between. Face aging, like you have a young age photo and you want to know that how you looks when you got 80 years old, and you can also able to create your young age photo to old age photo. This is process is called aging. So these are some application like image blending. You have these images, you cut some portion of this image from that, put on top of this, and how smoothly it is blending these images from here to here. So these are some of the useful application of the GAN. So I think it will provide you a better motivation to learn this particular subject, and it is one of the good innovation of this century. And after the innovation of GAN, there is a lots of work and research are growing in the domain of the unsupervised learning. So by this you can assume the power of the GAN. Now we can move further on the working of the GAN. So GAN is basically a neural network, which I discussed previously. But GAN is made up with a two neural network. The first neural network is called generator, and the second neural network is called the discriminator. I can also specifically write here GAN created with GAN is created with two neural network. One is a generator, second one is a discriminator. Now question comes in your mind is, what is this generator and what is this discriminator? So before starting to discuss about the concept of generator and discriminator, I will want to giving you some real life example, and I think you can able to understand the concept you betterly using this example. So let's consider a two person. Let's consider the two person. Let me take it right. So this is a person number one and this is a person number two. Person number one is a thief, means chore, and the second one is a detective. Person one is a thief and person two is a detective. Now this two has two tasks. The task of person one is to make a fake currency, means the task of thief is to generate a fake currency, and the task of detective is to classify this fake currency into a real currency and a fake currency. So there is a two person. I am again repeating, there is a two person in the picture. One is a thief and the second one is a detective. One is a thief, second one is a detective. Task of thief is to generate a fake currency, making a fake currency. Task of the detective is to classify this currency into real or fake. Let's say you provide some currency note to this, then the detective task is to identify whether this particular currency is a real currency or fake currency. Till the point I think the concept is clear to you. So what is our task is to thief can able to create a generate a currency in a such a way that this detective cannot able to distinguish, means it got confusing the identification of this generated currency. Okay, so let's take one example. So initially let's say this thief is created some currency and passes to the detective. Initially thief has a no knowledge. Initially he has a nothing no. So the initial results of generated currency by thief is very good. So initially it cannot able to generate a good currency, able to generate good fake currency. Means initially it is easier for the detective to identify this generated fake currency. Throughout the time, let's say first time it generates some currency, initially it has no knowledge about it, so it generated a very bad fake currency and it can be easily identified by anyone. Passes to this detective can easily identify and saying that it is a fake currency with the probability 0.9, and this is the probability. Okay, the currency, so here we can show that it is easily classify it as a fake currency. Let's say again you feedback backward to the thief. Now it can learn from some of the mistake which is made in the previous step. Now it can try to generate some good level of fake currency so that it is difficult for the discriminator to identify. So let's see in the next step it generated one fake currency, and now this probability is from 0.9 to 0.8 and 0.2. So now we can say that it is generated a better currency as compared to the previous stage, because in the previous stage it is saying that 0.9% it is a probability that it is fake, but now it is saying that probability of fake is 0.8, means we got a quite improvement in the performance. Throughout the time passes to this, it can classify back to the feedback again and again and again and again. This circle is repeated, and let's say after n number of time, after n epochs, means after not n epoch, after n cycle, thief is able to generate a currency in such a way that this detective cannot able to distinguish between real and fake. Cannot able to distinguish between real and fake means the probability of the probability of real is 0.5 and probability of fake is got also 0.5. Means it got confused to identify whether it is a fake or whether it is a real. Now our thief task is done, because by looking into the note, the detective cannot able to differentiate between the real and fake. Means the thief training is done, and now it is ready for the generating a fake currency and deploy the fake currency in the market. Obviously this is not ethical task, but we are taking it as at an example. Second question comes in your mind is, how detective know that the currency is fake or not? How he know? Okay, so for that, let's say we already have some data set of which contain the real currency and the fake currency. Using this data set, we can provide a training to detective, so that detective can learn and differentiate between the real and fake currency. I think something got very mixed to you, so I can again repeat the process. What is our task is, in the picture there is a two person. So in the picture two persons are there. I am clearing this for you. Okay. So in a picture there is a two person. One is a thief, second one is a detective. Task of the thief is to make a fake currency, and detective task is to classify this currency into real and fake. Now detective has some data. How we have some data set of real and fake currency. By using this data set, we can provide a training to the detective, so that it can able to identify whether the currency is fake or whether the currency is original. This dataset contain original and real, so we provide this dataset to detective. From this dataset, detective learn the feature of the fake and real, and using this knowledge it can able to identify the note generated by this thief is real or not, real or fake. So initially thief has a no knowledge, so it generate a bad quality currency, and it is very easy for detective to identify in a fake and real. Likewise it shows 0.9 and 0.1. But let's say first time it's got failed, second time, and then this, and then third time, then fourth time. So after nth cycle, let's say thief has a good amount of experience and good amount of knowledge in generating a fake currency, and now it generate a currency and passes to the detective. Then detective got confused, and it says that it cannot able to differentiate between the real and fake. Means the real and fake looks almost similar for the detective. Means probability of fake is 0.5 and probability of real is also 0.5. So this is our entire task. So how it is applicable in the real world? So means how it is applicable in the GAN. So I hope till the point everything is clear to you. So in GAN we'll also have the similar process. So let's take one example. Let's say you want to generate cat images. I will write some task is to generate the cat images. Again we discuss in this, the data generated by the GAN is similar to original, but not same. Similar to original data set, but not exactly same. Okay, so you remember this. So our task is we have to generate a cat images. For that, let's say we have some number of cat images. We have some cat images, let's say 1000 images. Okay, so in the GAN I mentioned that there is a two neural network working inside the GAN. One is a generator and second one is a discriminator. So now we are going to understand the concept of the generator and the discriminator. So you can relate with the previous example. This generator is a thief and this discriminator is a detective. Means thief in our example is generator and the detective in our example is this discriminator. Now you can able to understand the task of the detective. If we are now we discuss in the terms of machine learning, then the task of this detective is basically, you can see, it is a task of classification. He has to classify in the two class whether it is a fake or whether it is a real. So one thing you can understand is this discriminator is a classification neural network. Because the task of discriminator is to classify generated data from the network is real or fake. So this discriminator is a typical classification task neural network. This generator is something new which is we not know. So what we can do is, the original data means, let's say, as I mentioned this, we have fake data and real data both. Based on that we train a discriminator. So discriminator has power to identify whether the generated data is a fake or whether the generated data is a real. So now in this we also have a original data set which contain the fake images of the cat. So this original data set is containing this original data set is containing fake cat images. So means this original data is containing a fake images and real cat images. This fake images is nothing but some random noise image. Let's say you have 32x32 image and you can randomly assign some pixel value to these particular images. So it has nothing similar, but you can generate these fake images from a Gaussian noise distribution and all. We'll discuss in the upcoming part of the video. So till the point I think the concept is clear to you. So in this dataset fake images are there and the real cat images. Based on that we train a discriminator. Now discriminator has power to identify between the real cat images and fake cat images. So I think discriminator task is too clear to you. Now what is a task of generator? We can provide some random noise, some random image to this some random noise to this generator, which is basically not a pixel values of vector which is we specifically call in technical terms this generator. This is again one neural network. So it has some layers inside this. What layer is we are not going to discuss right now, but it has some layer inside this. It can convert this random noise to some realistic images and passes to the discriminator. Now discriminator task is to identify whether it is a cat image or a noise image. Means if it is a cat image, then it is saying that yes, it is a cat image, and if it is a noise, means the generated image means the image generated by this generator, it is not good quality and different. This discriminator can easily identify between real and fake. Means we have to train a network. So what we are doing is we performing a back propagation to adjust the weight of this generator. So using the back propagation algorithm, and I assuming that you all are familiar with the back propagation, so I am not going to discuss back propagation in this video. I am just giving you a intuition about it. Like when you passes the data to your network, this like random images passes to this. Now it is processed through some neural network, it gives some output. Now it is passes to the discriminator, it's process something in this and calculating this probability of real and fake. So this entire process is called the forward propagation. But you also know that in the first step, means in the one cycle, you cannot get good results. So based on this output, you can back propagate on this and you can adjust the weight of your generator, means weights of your generator and discriminator, such that it is we can got a good result. So this is the idea of this. So using the back propagation algorithm, we can adjust the weight of this generator so that it can able to generate a good quality of fake images, good quality images. Okay, so throughout the training process is happening, we can forward propagation, then back propagation, then forward backward, forward backward, forward backward, forward backward, forward backward, and for after a certain number of epoch, let's say 1000 epoch or 1 lakh epoch, your weights is adjusted. And now if you pass if you pass generated images from this generator to the discriminator cannot able to distinguish between the whether it is cat images is real cat images or it is generated by this generator network. So now our task is complete, means the probability of both is 0.5 and 0.5. so this is our task. Is at this particular time we can say that our generator is ready to generate the cat images. Now we cut this entire network. Passes some random noise to this generator G, which is basically this one, and it is giving you, we basically cut this portion, and now we don't need discriminator because training is done generator, and now it is giving a cat image. So this is a overview of the GAN, that what we are doing in the GAN, what is the concept of generator and what is the concept of discriminator. I hope till the point everything is clear to you. So till the point everything is clear to you, that's I am hoping. For the next part of this video, we are going to discuss about the loss function of the generative adversarial networks. So I'm again repeating some of the things which we will discuss in the previous part of the video. What is the objective of the discriminator is to classify between the real and fake data set. So discriminator objective is classifying the data set between real and fake. It is a binary classification problem. What is the objective of the generator? The objective of the generator is generate a fake data in such a way that it is fool the discriminator. Means the generated data from the generated data from the generator, it is looks almost similar to the original data set. So it will be very difficult to identify for a discriminator whether the generated data is real or fake. That means we can say that the probability of generated data is 0. What we can say is probability of real and probability of fake both equal to 0.5. So that's how we can able to fool the discriminator. And now this is our entire objective. Now let's discuss these terms in more of the mathematical ways. So let's say this is a distribution of the original data set. This is the original data set. I write also here real data set. Okay, so let's say this is the distribution of the real data set, and this distribution name as D. Okay, this is the distribution of random noise, which is where somewhere pick up from the Gaussian noise or anything. So this is a distribution of the random noise which is named as Z. This thing is clear. So for the generator you remember the data from the real source is also input, and data comes from the generator is also input for discriminator, not generator. For the discriminator there is a two input sources. One input source is this real data, second input source is this generated data which is generated by this generator. So initially firstly generator has this generated data, then real data, then it has this generated data. So basically generator also produces two output, one output for the real data and the second output for this generated data, and this is basically a probability. Okay, so when the data from this distribution D is coming here, which is named as x, so this is a generator function which take x as an image, and it has some parameter, means theta D, which is a trainable parameter of discriminator. So the data x is coming, and using these parameters it can produce a probability that D of x. This is for this original data set. Another data is, let's say we have this distribution, we pick up image passing to this. So passing to this means this is a generator function which take a image as a input, and it has a generator function parameter which is a theta g. So using this parameter and image, it output the generated image which is called as gz, because it is generated from G and it is input source is Z, means let's say from this big Z we can give small z as input. So this is here, so this small z is passing to the generator. So generator generates G of small z, means it is a generated images. This basically is showing that it is a generated images. This generated images is also passed to discriminator, and the prediction corresponding to this generated images is called D of Z of Z. Whatever images we are coming will passing to discriminators. Let's assume discriminator is a one function and let's take one argument. In the case of real data, what is coming here? X, because here we are passing this X. In the case of generated data, what we are passing? D of G of Z. That's why here is coming D of G of Z and here is D of X. This terminology I think is clear. So let's say you have this distribution of real data set and you want that your data which is generated from this generator is also similar to this distribution, so that it is difficult for the discriminator to identify or distinguish between this generated data and the real data set. So initially this is our random noise distribution, we pass it to generator, and let's say we train this generator for the 10 number of epochs, and as a output we got this type of distribution. Now this distribution is passing through discriminator, and for the discriminator it is very easy to identify that this is a fake, because these both are nowhere look much similar, so it is easy for generator to classify. Now for like this is for 10 epoch. If we train for the 100 epochs, then for the 100 number of epoch, let's say the distribution is look like this. This is not exactly similar to this, but somewhere it is similar. Let me make it quite different so that it will be good for your understanding. Okay, so it is also quite different from the original distribution, which original is here and generated is here. Again you pass this generated distribution to this discriminator. Again it is an easy task for discriminator to distinguish between real and fake, and it is simply say that it is a fake. So this is a distribution of entire data, and this point represent the individual images. So we are basically, what is this is, we are not taking a single sample at a time, because you know that in the deep learning, instead of taking a single sample, we are passing a batch, like 128 size batch, 64 batch size, 32 batch size. So we are passing the images in batch. That's why it is a bunch of the images, not a single image. Again you train for 1000 epoch, got it this distribution, passes to discriminator, and again it is easily distinguished between the real and fake. And after a certain period of time of, let's say, training for the 10,000 epoch, and you got this distribution which is more or similar to this real dataset distribution, and now if you are passing this to this discriminator, then this will giving a probability of D of Z is equals to 0.5, means probability of fake equal to 0.5 and probability of real is also 0.5. and now our task is done, and the generator is able to fool the discriminator, and this is the end of the process. So let's say this generated distribution we represented by P of G. G means generated, of G of Z. Why G of Z? Because this individual image is generated by the G of Z. Let's say we pick up this image, passes to generator, and it gives some output which is represented by g of z. So it is a individual images, but if we take a distribution of this, then we can take like this p of g, which is probably distribution of generated images, and what is this, which it's contain a z of z type of images in this. Basically this is the z of z individual sample. I hope this thing is clear to you. Understand this terminology because it will be giving you a better idea in understanding the next part of this particular video. Now I write something here. This d and z means d is this one and z is this one. These both are the distribution of the real and random noise. So d is a distribution of the real data set, z is a distribution of the random noise. Objective is what we want, that the distribution means generated data's distribution p of g of z, this distribution is equal to the p of data of x. The p of data of x is original distribution. So the probability distribution of this and this, we want that these both are similar. We want that this both distribution are similar, so that it is difficult to identify for the discriminator in real and fake. Now what is our task is p of g of z equal to p of d of data. So eventually what we are trying to do is, if we pick up some sample from this distribution is also one sample means this is, let's say, your distribution, and you pick up randomly any one sample, so it is a more or less look like x. What is x is one randomly pick up sample from the real data set. What is g of z is randomly pick up sample from the generated data set distribution. So eventually we are trying to do this, means these both are more or less similar but not equal. This is the objective of our task. I hope this terminology is clear. I am again repeating this to you. We have real dataset distribution and we have fake dataset distribution. We will passes the fake dataset to generator. Generator generates some kind of images. It is not proper at initial state, but it generates some kind of images. So this real images and this generated images both are passing to distribution. So this corresponding to this both, we have two output. For the real images we have probabilistic output of d of real images. So this is basically d of real images, and corresponding to this generator data we have probabilistic output which is d of g of z, means it is d of generated images. Okay, and we want that these two distribution are more or less similar, so that it is difficult for identify for a discriminator between real and fake sample. Till the point everything is clear to you, that's I am hoping. Now let's we are doing a classification task. So you all are aware of the binary cross entropy loss function. So the formula of the binary cross entropy loss function is loss of y predicted, and y is y log of y hat plus 1 minus y log of 1 minus y hat. This is a loss function of the binary cross entropy, where the y is an actual label and y hat is a predictions. Okay, so I discusses in the GAN we have two neural network. One is a discriminator D and the second one is a generator G. So now you understand we have to calculate the loss for this both, ones for generator and ones for a discriminator. So let us first try to calculate the loss function, objective function for the discriminator D. Sorry if I am making some mistakes. Sometime I am calling this discriminator as generator, but it is by mistake, so sorry for that. So calculation of loss for the discriminator D. So again what we'll discuss so far is discriminator has two input. One is a x, which basically I say this is real data, and gz, which is a come from this generator. So it is a fake data. And why it is called gz? Because generator, we call generator is g, and generated image generator, we take generator as a function, then the image generated by generator is g of z. That's why we call it g of z, and x is not anywhere generated from any other source. That's why we call it x only. discriminator, his objective function is d, is take image as an input and it has a discriminator parameter theta g. Using this parameter, it calculate the d of x and d of g of x. Okay, so I'm repeating this 3 times, so I hope this point everyone is familiar and better understand, so I'm not going deep into this much more now. Now what we'll do is, the label come from the p of x is 1 and the prediction is d of x. What I'm trying to say here is, if you take a data from p of x, what is p of data of x? P of data of x is this distribution. If you take any image from this, so we know that this is a real data set. So corresponding to real data set, we have a label y equal to 1. Okay, this is understand to you. Corresponding to this data set, we have label y equal to 1. We pass this data to this discriminator and we got this d of x as a prediction, which is equals to y hat. Okay, so everything understand to you. The data which is taken from the real data set has label is y equal to 1, means it is a real data set, and corresponding to real data set, we got this output as a y hat from the discriminator. Why discriminator? Because we are calculating a objective function for the discriminator. So now we will not going to discuss generator in this, we are only discussing about the discriminator part. So what is this? P of data of x is 1 and prediction is d of x, means this is a y hat is d of x. So we simply put it into the binary cross entropy equation, means L of 1 comma d of, sorry, not this, L of d of x comma 1, and calculate, put the entire value in this, means put y equal to 1, then this 1 minus 1 becomes this 1 minus 1. If you put y equal to 1 and y hat is equals to d of x in this particular equation, then here it is 1, and in this y equal to 1 minus 1, because y is equal to 1, then this entire term is got 0 and this term is cancelled, and we are only left with this log of y hat. So this is a calculator, we are only left with term log of y hat. What is the value of y hat? Y hat is d of x, so simply we put it here, then we got our first objective function as log of d of x. This you can say equation number 1. Till the point everything is clear to you, that's I'm hoping. So what we completed this channel only. We have to calculate loss for this channel also. Okay, so for this channel, what is the input data? This g of z. What is the corresponding label to this g of z? Corresponding label to this particular g of z, y is equal to 0. Why? Because it's come from the generator, and generator, we know that the data is a fake data. Generator generate a fake data which is similar to the original data set but not exactly same. So that's why label corresponding to this all g of z is 0. So in this case, what is our y is equals to 0, and what we get as output d of g of z, means this is a prediction. So this is our y hat value. That's this is I written here in the form of text. So data come from the generator label as 0, means data g of z are assigned label as 0. Okay, so means we have y equal to 0, means actual value is 0, and y hat, what we get as a prediction in terms of probabilities, d of g of z, means d of g of z is a prediction. Prediction means y hat. So if we simply put the value, this is a y hat and this is a y, so y hat and y in the loss function, and put the value of y equal to 0 in this particular equation. So if you put y equal to 0 here, then this entire term is got 0. If you put 0 here, then it become 1s and will remaining with log of 1 minus y hat. What is the value of y hat here is log of 1 minus d of g of z. So this is the objective function corresponding to the second channel. This is the objective corresponding to channel number 1. This is the objective function corresponding to channel number 2. We can assign as equation number 2, and this is equation number 1. Till the point everything is clear to you. Okay. The objective of discriminator, I am again repeating something. The objective of the discriminator D is to classify between real and fake data set. Now the question comes in your mind is, we have this equation number 1 and equation number 2. Generally what we are doing is, in general, in the terms of machine learning or deep learning, what we are doing is we are optimize our loss function to the minimum loss. Okay, this is our target. We are optimizing our loss function, means minimize the loss function and getting a best parameter value at that particular minima point. That's we are doing in the training process. So from these two equations, how we are getting a best result for the best parameter for the discriminator D. So how to achieve, means how you can train the discriminator using these two objective function. So what we are doing is, it has a two channels, so let's club these two equation. So this is equation number 1 and this was the equation number 2. We can simply add this, means we are clubbing these two equations. So what we want is, for generator perspective, this d of x is come from the real data set, that we know. For the real data set, what we want is, so for the real data set, our prediction is d of x. For the real data set, what we want is, predicted value is also 1. So means d of z of z, we also want that it is become 1. The objective is clear to you. For the generator function channel number 1, if we are passing a real data set, so what our expected output from the discriminator is, if we pass this sorry, I am again confusing, sometime calling discriminator as generator, so sorry for that. But if we are passing a original data set to the discriminator D, then what we want is, it can classify it as a 1 because it is a real data set. So our objective for this particular task is, and means is classified 1, means y prediction equal to 1, and means y prediction is equals to d of x is equals to 1. So eventually we want that the d of x is becomes for not near to 1, like 0.9 or 0.99, 0.97, near to 1. So if we plot the graph of log of d of x, means if you plot the graph of log of x, then here is the graph of the log of x. So this is a graph of log of x, or we can, in our example of log of d of x. So we replace x with d of x, not doing nothing. So where we got the maximum value? So the question comes in your mind is, we cannot find the maximum for this because eventually this is increasing till the point, and we cannot able to find the maximum value. Yes, you are right at your point, but I saying that this is a probability value. This is also the probability value corresponding to the generated data. This is a probability value corresponding to the original data set, and we all know that the probability value lies between close interval 0 to 1. Okay, so we all know that the probability value lies between close interval 0 to 1. So there is no meaning of considering this particular reason, because here the values are greater than 1. This point is basically 1. This point is basically 1. So we are not considering this part for finding our maxima. So now our area of interest is from here to here. So these all values, you already see that this is a negative. At this particular point, we got a maximum objective value to corresponding to this. Why we are getting maximum value here? Because d of x is a probability. and we can know that the probability range is in between 0 and 1. So the values are from 0 and 1 only become input for this log of d of x. We cannot take a more than one, like we cannot put 2 here. Why? Because if you are taking a log x graph, then you can put 2 here because it is log x. But if you are log of d of x, means it is a probability, and you cannot take a d of x as 2 because it's violate the rules of the probability and all. That's why our area of interest is this region only, and here I got d of x is equals to 1. For this particular function, what we want is generator classify this generated data as 0, means y prediction is equals to 0, means d of g of z equals to 0. If we are drawing a graph of log of 1 minus x, then it seems like this. Here is 0.1, this is 0. So this is the graph of log of 1 minus x. The graph of log of 1 minus x look like this. What we want is d of g of z equals to 0 for correct classification. We want d of x equal to 1 for the correct classification and d of g of z to 0 for correct classification. Where we got d of g of z equal to 0? At this particular point. Now again picture comes that here we cannot consider this area. Because here it is less than 1, and here it is greater than 1. So we are only interested in a region in between 0 to 1, means this region for this particular graph and this region for this particular graph. We are only taking these two regions. So where we are getting the value of d of g of z equal to 0 at this point, and we are getting value of d of x equal to 1 at this point. So eventually what you can see, if you consider an area of interest of area of region in this particular point, then these 2 points are the maxima of these 2 functions. For if you consider this as one function and consider this as second function, then this is a maxima of the first function and this is the maxima of the second function. So by finding the maxima of these 2 particular objective function, we can achieve our goal, that's predicting d of x equal to 1 and d of g of z equal to 0. So here I written is, for generator we want d of x becomes 1 and d of g of z becomes 0. So we can achieve this task by maximizing the objective function. By maximizing the objective function means it is, if you are maximizing this entire function, so our gradient for maximization we are simply using a gradient ascent algorithm. So our gradient ascent algorithm force to convert d of x to 1 and d of g of z to 0, and using this, by maximizing this, means we are forcing d of x to become 1 and d of g of z to become 0, and eventually it helps to identify in a better training of the discriminator d. So that is our objective function for the discriminator. So here I written his discriminator objective function d is equal to maximize log of d of x plus log of 1 minus d of g of x. This we can say as equation number 3. I hope till the point everything is clear to you. Now again I started GAN is made up with a 2 part. One is a generator and second one is a discriminator. So we done with the discriminator loss function part, so we put it on side, and now comes on this generator portion. For generating a loss for the generator, again we are repeating some previous thing. What is the objective of the generator? Objective of the generator is to fool the discriminator such that it cannot able to distinguish between real and fake images, whether it is generated by a GAN or it is a real images. Okay, so this is the objective of the GAN, to fool the discriminator. For that, fooling the discriminator means what? In the generator, if you remember that this is our discriminator, we are passing generated data d what is this, g of z to this, and eventually we go, I only plotted one channel here. D of x is also there, x is also coming. We are not considering this right now, but we are only taking this channel for now. So if you taking this channel, then you passing d of z and you getting output as d of g of z. So what is this? D of G of Z is the probability of a real versus fake. Fooling a discriminator means D of G of Z is fake data. This D of G of Z is fake. This D of G of Z is fake data. Means actual label corresponding to this is 0, but somehow generator able to generate a data in a such a way that it classified as a 1, means real data, by the discriminator. Means that's what generator want to fool the discriminator. Fooling means it want to cheat with the discriminator. So generator generated fake data passed to the discriminator, and if discriminator classify it as 1, then we can say that generator is successful in their task of fooling the discriminator. So that is our objective. So fooling a discriminator means we got this output as 1 or near to 1, like 0.997 or 0.99, 0.98, something this. So this is our objective. We are want to fool the discriminator. For that we want D of G of Z is equals to 1. G want to, so means generator wants that the discriminator produce probability D of G of Z corresponding to fake data is 1 or near to 1. So this is generator want. If we are again put the actual label corresponding to generated data is 0, we know that the generator generating fake data, so the actual label is always 0. If the discriminator somehow generate that data as 1, then means the discriminator not get full by generator. So again, what is the value of y is 0, and y hat is D of G of Z. If we put in the equation of the binary cross entropy loss function, then y hat as D of G of Z and y as 0, and we again got this particular expression. Now you can see that there is while training a discriminator, we are considering a 2 channels, shown here is we are considering a 2 channels, channel 1 and channel 2. So that's why the both of the terms is log of D of X and log of 1 minus D of G of Z. Both terms are contributing in the training of generator, means real data set also contributing and fake data set is also contributing in the training of generator. But when it training of the discriminator, I am again calling a discriminator as a generator, sorry for that. But when we are training the discriminator, the only terms will dominate is this one, because in discriminator we are training generator, so we'll pass it to this, and this is from then generator G, this G of Z, and this is the output. So we are only considering this channel only. So for this channel we are not considering the second channel for the loss function of the generator. For this one channel only we got this as an objective function. So this is an objective function corresponding to the loss. Now again we plot the graph of this, which is similar. What is our objective now is we want to make D of G of Z is equals to 1. So D of G of Z is equal to 1 at that point. What is this point? If you are going to this, then this we can say that this both graphs are meeting to each other at point minus infinity. Minus infinity means it is a minimization task. Minus infinity means it is a minimization task. So our objective function is becoming this: G is equal to minimize log of 1 minus D of G of Z. This is all about it. But for the mathematical simplicity, we are include this term also. Again, this term is no significance in this, but if you club the generator and discriminator for loss function at once, then by including these terms we are simplifying the mathematical equation. So we are only considering this for the mathematical simplicity. There is nothing use of this while training of the generator. So basically it's independent. If you back propagate and differentiate it with respect to this, then the differentiation is also got 0. So that it is nothing important in generator, but we are using it only for the mathematical simplicity. So combining the objective function of the discriminator and generator, so what generator is doing is, what first discriminator is doing, discriminator is maximizing these two terms. So that's why we write maximize corresponding to discriminator these two terms, and minimizing these two terms for corresponding to threes. So while training of the discriminator, these two terms are contributing, but while training of this generator, means this minimization task, only these term is contributing. Although if you consider this, but while it is procedure the back propagation algorithm, so the differentiation corresponding to d of g of z, d of x with respect to these term is also got 0, and eventually this is not any effect on that. So that's why we are considering this. But you have to remember this, for the discriminator part we maximize this entire expression, whereas for the generator part we are minimizing only this part, we are focusing only this particular part only. But this entire expression is again, I can say that this d of g of z is single images. If you have to in a previous I simply showing you one diagram here is, so if you look here, this d of g of z is single images, and if you consider this entire distribution, then we can represent it as a terms of p. So it is an entire probability distribution p of g of z. Okay, and we eventually try to make similar this both distribution by training a generator and discriminator. Then comes to our actual point. So this equation is corresponding to only one images or only one data point. If we perform this entire equation again and again for the many times over the distribution of this real data and this fake data distribution corresponding d and z distribution p of g of z, then if you perform over the entire distribution, then we have to use the concept of expectation. So we simply just write e in terms of here. So here we consider the expectation of x, where x is come from the original data. P data means original data, and here the z, here is this z is come from p of z. P of z is what? The distribution of this generated data which I mentioned here. So this I written is p of g, but it is p of z. This is p of z, and this is p of x data, real data x. This is this both distribution, means optimizing the loss function of the GAN, minimizing the maximizing discriminator. This x in this particular term, x comes from the real data set, and here the input image or input data point is come from the generated data set. This is a loss function of the generative adversarial network. I hope till the point everything is clear to you. So that there is one more concept I want to discuss here is, again we also simplified this loss function in the paper of this Ian Goodfellow. It write, and this is an algorithm, and it is also writing entire is also writing the entire proof of this by integration, applying some mathematical theorem on top of it, proofing this equation. But we are not going to discuss this part also. I am going to discuss this part, and I request you, everyone of you, to read this paper once after watching this particular video. So I am discussing this graph. So in this particular process, what's happening is, I'll explain itself here. So in this particular process, what's happening is, initially this is a distribution of the real data set. Let me reduce the pen size. This is a distribution of real data set. This is a distribution of fake data set, and this is a line of our discriminator function. Okay, so in this particular, the real dataset and fake dataset distribution are clearly different. That is visible to you that this both distribution are different. What I do is I'll simply go on this and explain here. Okay, so here you can see that the real and original dataset distribution is clearly different. So you can easily identify so it is easy for the discriminator function to identify between real and fake. From moving from this A to B, what we are doing is train discriminator D. Now you see that the discriminator D line is got changed, and D is good and smart enough to classify in between real and fake dataset. Here is like this, but now D is become more smooth. Again, we are not touching any distribution. From A to B, what we are doing is training a discriminator D. So D is got changed. So from here to here, what we are doing from B to C, moving from B to C, we are training the generator. Training the generator. So first we are training discriminator. It change the line of discriminator. Then we are training generator. Generator training means it is able to generate a better fake dataset. Generate a better fake dataset means distribution of the fake dataset is more or less close to the real dataset. And here you can showing it. This is a distribution of fake, and this is real. Now it's become more closer compared to this previous one. After this step, if we repeat this process again, then at a certain point of time we got generated data distribution and real data distribution same, and at that particular time we got our discriminator function, objective function line is this. Basically here it's showing that the probability P is equal to 0.5, means the generator is fool the discriminator and it got confused because it's giving a probability as 0.5. So that is our entire objective. Now we'll discuss this algorithm for this particular GAN. So let's write the algorithm from the scratch. Steps. So what we are training is, in deep learning you know that we are not providing entire data set. Instead of this we provide data in the batch, in the batch size. Okay, so we starting a first loop for I in epochs, then for j in the batch number execution, means how much times, if you let's say if you have 1000 data point and you divide in the batch size of 10 data sets, so each time 10 sample from this your 1000 data set pick up and will process it. So how much time we repeating for the each epoch, we are picking a 10 samples. So if you divide 100 by in n, this n is equals to dataset length divided by batch size, which is 100. So in this case n is 100. This is terminal of significance of n. So I want to discuss the algorithm discussed in the paper itself, so we'll write properly. This is the first, and for j in n, what is n? I explained to you here already. What we are doing, pick m number of sample from real data set. This is the first step. Pick m number of sample from fake distribution, means fake data set. Provide this to discriminator D, real and fake both. Update the weight of discriminator. Now what we are doing is pick m random noise sample update weights of discriminator, update the weight of generator, generator G, and repeat this process. So I think this would be not clear to you. I understand that initially it is not clear to you. What we are doing is, for that let me draw a diagram again. So here is our discriminator D, here is our generator G. Discriminator has two input. This is a real data, this is a generated data, and it giving you a output as 0 or 1. It has some random image noise. It has some random noise data set here. So this is a real data set come to generator. Initially what we are doing is, first we are, instead of, if you are going to train this generator and discriminator both simultaneously, then eventually you are not getting to end up with the good results. So what we are doing is, firstly we are individually train discriminator. So discriminator task is to identify between 0 and 1, binary classification. So what we are doing in individual training of this discriminator, we are providing a m number of real images and m number of fake images. If you only provide real images to the discriminator, then it is no point of training, because we only see the real images. Then you can provide anything, it give output as real. So we have to provide both type of images to train the discriminator, real images as well as fake images. Using this we train discriminator. This is for one epoch and batch size. Now discriminator is trained on the real and fake images. Now generator comes from picture. So what we are taking is, we are providing some random noise to generator. From the random noise, generator computes some computation on top of this random noise and give us some output image, means some output data set. And this output data set is passed to discriminator. Discriminator this classify this output data set in whether it is a real or whether it is a fake. Okay, so what we are doing is, in the second step we are training generator. For that what we are doing is, pick m random noise sample, provide it to generator and classify it using a discriminator. So based on the classification output, we will back propagate and update the weight of generator. Note this step, back propagate, update the generator. So while training a generator, we are freezing the weights of this discriminator. Means once the discriminator train here in a loop, now we are not updating this discriminator. And in the training of generator, we pass this data to this entire channel, and back propagating means this weight is not updated in this back propagation process. Only the generator weight is got updated. This weight has no updation in this. So here I write this process for each epoch. In each epoch, firstly we train generator. For in each epoch, what we doing is train discriminator, then train a generator by freezing weights of D. Means we are not touching the weights of D somehow while training this generator. It is something like transfer learning. Likewise, in transfer learning, if you are using any predefined architecture like ResNet or VGNet, then you are not touching the weights, already pre-trained weights of ResNet and VGGNet. You are only training your lower level layer, which is closer to the output. We are only training this layer, but this VGG layer we can untouch. We cannot training this layer. We use this weights value as it is and connect it through some fully connected layer and getting a output. So this somehow we are doing these kind of processes. While training a generator, we can provide data set and then generator able to distinguish between 0 and 1. After training a generator, we are training this discriminator. Discriminator we are training and then calculating a discriminator loss. But while back propagation of discriminator, we are freezing the weights of generator. While back propagation for this generator, sorry, I am again confusing between generator and discriminator, sorry for that. While back propagating, we are not touching the weights of this D, we are only updating a weight of this G. This is how the training process of GAN is work. I hope this video is clear to you and you can able to understand. Now in the next part of this, we are trying to train again on CFAR 10 dataset. So for that we are going to jump on our laptop screen and showing you the coding implementation of generative adversarial network, that how we can able to generate a fake images.